You. Okay, mutually exclusive events. Have you heard that term from me yet? No? Okay, good. Right, what do we say? Well, suppose you have two events, A and B. They are mutually exclusive. I'll just call it ME for short. They are mutually exclusive, means that they do not share any common events. So I'll give you an example. Suppose A was throwing a dice and getting even number, and B is throwing a dice and getting an odd number. Would you agree that those are mutually exclusive, right? In one set, you've got the 2, 4, and 6, and in the other side, you've got the 1, 3, and 5. Do you see that they are mutually exclusive? They are separate groups. How about that as a kind of layman's way of saying it? Agreed? Now, can you remember the term, the complement of an event? That's a fancy way for not the thing, right? So you've got A, and then you've got it's not A. So it rains or it's not going to rain, right? That kind of thing. We typically call this guy AC when you look at it, you know, when you look at it. Do you know that the event A and AC are mutually exclusive? They have to be, don't they? If you're in the first group, isn't not A a total second group that share nothing in common with each other? A being male, B being female, probably could be examples of mutually exclusive. Here's two events: A being a woman, and B being a doctor. Are they mutually exclusive? Is event A being a woman and event B being a doctor, are they mutually exclusive?
Thankfully not.
No.
Right, and the reason they're not mutually exclusive, aren't there some women who are doctors?
It's because they can both.
Yeah, you can be both, right? So if you can be both, then you're not mutually exclusive. If you can't be in both, right? If there are two things where you can't be in one and in the other at the same time, then that's another way of looking at mutually exclusive. Are we comfortable about what mutually exclusive means then, right? Two distinct groups of things that share nothing in common. Okay. So let's look at probabilities then that have two events that are mutually exclusive and then two events that are not. And here is a formula for it. If A and B are mutually exclusive, then the probability that you get A and B happening is simply just the probability of A added to the probability of B. So if you want to find out what's the probability that A and B happen, right? Or A, excuse me. That is and, but the word I should have been looking for is A or B. My apologies. So what's the probability that A or B happens? It's that guy plus this guy. So if A and B are mutually exclusive, the probability of A or B happening is this. Well, suppose A then is, we'll do a card one. A is getting clubs and B is getting hearts. Then the probability you get clubs or hearts dealt to you. So somebody deals you one card. What's the probability you get clubs or hearts? It's those two things added. So that would be probability of clubs is 13 out of 52. The probability of getting a heart is 13 out of 52. So you can add them together. Oops. You can add them together, simplify, and as a decimal, you get 0.5. So if two events are mutually exclusive, you can get the probability of one or the other by just adding their individual probabilities together. On the other hand, if A and B are not mutually exclusive, then the probability of A or B happening is the probability of A plus the probability of B, take away the probability of getting A and B, which is, in English, the probability you get both. Well, let's do an event where that has happened. Let's suppose A is hearts. And let's suppose B is getting kings. Hearts and kings are not mutually exclusive. Can you be a king and a heart at the same time?
Yes.
Yeah, in fact, the king of hearts is that, right? That's an example. So if you want to get this probability, then you have the probability that you pick a heart, which is 13 out of 52. The probability that you get a king, which is 4 out of 52. Take away the probability that you get both. Now, in this case, how many kings are hearts?
1 out of 52.
So, right, so 1 out of 52. Now, do you notice that in this question, the bottoms are always going to be the same number? So you're basically just counting and subtracting. So 17 take away 1 is 16 out of 52, which if you do a 4 on that is what, 4 over 13. And if I can find my calculator, I will turn it into my usual decimal. So 4 divided by 13, and you get about 0.31. So about 31% of the time, if you're dealt one card, it will be a heart or a king. So if you're playing some kind of gambling game and getting a heart or getting a king would be enough for you to win, then that event is going to happen about 31% of the time. Of course, that event is not going to happen the other 69% of the time. So if you're a gambling person, can you see that your chances of winning are not as good as your chances of being beaten? So that might influence your decision about how you would gamble. Are we good? Let's try another not mutually exclusive. Suppose A, cards are really good for this, is red, and B is a queen. And we would like to know what's the probability that you get a red or a queen. So basically that's your A and that's your B, right? Well, it's going to be the probability that you get a red plus the probability you get a queen, take away the probability that you get both. And let's see what the partition is. Out of 52 cards, how many are red? Because that's going to be your probability of getting a red.
26.
Okay. Would you agree that there's 4 queens? So the probability of Q, the queens, is 4 out of 52. Now, out of the 52 cards, how many are red queens? That's kind of how I would say it to myself.
2.
And you can see in this case, the answer is 28 out of 52, which cancels down, I believe, to 7/13. And that, as a decimal, is about 0.54. Now, if you imagine this again with some kind of gambling game, the probability that the next card that I get, handed to me is a red card or a queen is going to happen, what, slightly more than half the time, right? 54% of the time. And if that's what I need to win, if I get that kind of card, I know I'm going to win this game. That's it. That at least is like a winning situation. Can you see that I'm going to win more often than I'd lose? 54% of the time I will win, and the rest I would get beat. Something else would happen that wouldn't allow me to win. Are we good with this mutually exclusive then, right? Two events that share nothing in common. If you want to get the probability of A or B, just add the two together. Very straightforward. And a little bit more complicated, if they are not mutually exclusive, then you have to use this adaptation formula. You still add the two, but then don't you kind of fix the double dipping by subtracting the probability that both things are happening?
Is the probability of both things happening, that's the probability of A intersection B, right?
Yes.
Okay.
Yeah, exactly. It's called A and B, A intersection B, and I'm just chucking in the word both as a very convenient way of just thinking of what they are, because essentially it's a computation issue anyway. So suppose I don't tell you who A and B are, right? But I do tell you that the probability of A is 0.3 and the probability of B is 0.4. And I tell you that the probability of A and B is 0.2. You should be able to calculate the probability of A or B happening. So there's no events. It's not kings and aces, red and queens. It's just pure numbers, but we can still answer it. Here's the first question. Are A and B mutually exclusive? And the answers will be yes or no, right? Imagine a question. Are they mutually exclusive? I can tell you right now that they are not mutually exclusive. And I can tell you that because this number isn't 0. If you think about it, if you're mutually exclusive, shouldn't the probability that you're in both be 0? In other words, it ain't going to happen. So if the probability of A and B, right, that's the probability of both, if that is equal to 0, you can assume that A and B are going to be mutually exclusive. Does the logic of that make sense? The probability of both things happening is 0. Isn't that telling you that those two things can't have anything in common? Because if they did, wouldn't the probability be something? It'd be a number, it wouldn't be 0. It'd be another number. So in this case here, wouldn't I be saying, I want this guy plus this guy, take away that guy. And in this case, 0.3, add 0.4, take away 0.2, and I believe you get 0.5. So you see in this question here, you don't even need to know a story, don't you? Just need to know that they're not mutually exclusive and that this formula here will allow you to calculate what you need. Because the question would be find probability of A or B. Here's a different story. Suppose I know the probability of A is 0.2, the probability of B is 0.5, and the probability of A or B is 0.9. I can find the value of the probability of A and B. And the way I'm going to do it is I'm going to start with this formula. And then I am going to write down all the things I know. I know this thing is 0.9. I know this guy is 0.2. I know this guy is 0.5. Ooh, ooh. Just change the number so it'll work. I'll make this 8, right? So that's 8. And then take away this guy. So what do I know? I know that 0.9 happens to be equal to 1, take away A and B. Okay, what decimal is probability of A and B? You can do it in your head. If this is equal to that, what does this have to be for that to be true?
0.1.
Yes. Isn't it a bit like solving an equation, even although it doesn't look like an equation? Subtract 1 from both sides and divide both sides by -1. Me, I would just look at that and say, okay, what do you need to take away from 1 to get 0.9? You need to take away 0.1, and now you've got it. So what does this formula here tell me? It tells me how the or and the and are connected. Right? You see that this basically ties together all the relationship. In fact, if I give you any 3 out of the 4, can't you always find the 4th missing one? So if I tell you the value of any 3 of these things, can't you always figure out who the 4th one has to be? Right? Just plug in the value and see what's left over. Are we good?
On that last problem,
Yes.
how do you know that the events are not mutually exclusive?
You don't care, because if they end up being 0, they are mutually exclusive. And if they end up not being 0, they are not mutually exclusive. So do you see this formula here? If they are mutually exclusive, won't that be 0, in which case you get the original formula? So this formula copes with every situation. So you don't need to worry, are they mutually exclusive or not, in this type of question, because that will sort itself out when you use the formula. If this had been mutually exclusive, wouldn't that just end up being 0 when it was finished?
Yeah, that makes sense.
In fact, I could imagine a question where they give you this, and then they don't ask you to find anybody. They just say, is this mutually exclusive or not? Right? Are A and B mutually exclusive? Now, you still do the same thing. You still get that. And then once you got that, wouldn't you say they are not mutually exclusive? So that would be a sneaky question if they did that, because at least the way I phrased it, you know what you're being asked to find, and you know you're always going to start with this particular formula. So we are looking at complex probabilities where you're choosing one item, but there's like 2 events. So what's the chances of A or B happening? That kind of complicated, complex event. And we also talked a little bit about mutual exclusive. Independent events. Now, independent events. A and B are independent events if the probability of A has happening has no effect on the probability of B happening. So if you can imagine two different events, right, A and B, and whatever happens in the first event has no effect on the probability of the second. So I'll give you a very simple example. Suppose I was throwing a dice and the other one was I was throwing a coin. And A was the event that I threw the thing and I got a 4. And B was the event is I tossed a coin in the air and I got a head. If I asked you, does the result of the dice thrown have any effect on the probability of the coin being a head? You should say, no, that's not going to affect this and this is not going to affect that. That would be an example of two independent events. Right? Now, there are various ways you can use that property, and there are ways that you can use, formula that you can use to test if this is true. So here's the first result. Now, this is two different events, A and then after that and B happening, right? So this is two events. It's a probability of A times the probability of B. It's called the multiplication property of independence. So if two events are independent, then the probability of one happening and then right after it, the other happening, right? So it's like two separate events. It's the same thing as multiplying the probabilities together. So for instance, in that very simple story I had here, the probability that you throw a dice and you get a 4, and then you throw a coin in the air and you get a head, is just the probability that you get a 4 from a dice and the probability you get a head when you throw it. Well, isn't getting a 4 from a dice 186 and getting a head when you throw a coin is a half? And so the answer you get here is 1/12. Does that make sense? So if two events have nothing to do with each other, the probability that both those events happen, right? A happens and B happens, right? So it's a two event deal. Is simply just multiply the two together. Now, if two events, A and B, are not independent, then the probability of A and B will not be equal to that guy. And we can actually, as you'll see later, we can actually use this to check for independence of two events. Now, it's easy to tell a dice and a coin have nothing to do with each other, but actually that's not the typical question. The typical question is that A and B are two events living in the same world, like throwing two dice or picking two cards from a deck, right? They're both events dealing with the same deck of cards and you're doing two things to it. Or, a dice and rolling it twice, right? So that's the kind of situation that we're going to get. So let's look at an event, or two events that are independent first. So suppose I have two dice. And A is, you get a 6. And B is, you get a 5. So what's the probability that you roll 2 dice and you get a 6, and then the next time you get a 5? Well, would you agree that if you roll the first dice, it doesn't matter what number that is, when you roll the second dice, won't it have no effect on its probabilities? So we know that because common sense tells us that they're independent. So we could make that assumption, and the probability of 6 times the probability of getting a 5 is what we would do. And aren't both of those 1/6? So the chances that that particular combination happen is going to be 1/36, which is a very small percentage. As a decimal, it's about 3%. So far, so good. Independent events, if you want to know the probability of getting, I could do anything I like. Do you know when you play a lot of dice games, don't you want to get a 6? You know, you go around the table, right? You want to play Monopoly, isn't a 6 probably a good thing most of the time? Right, would you agree that that's just going to be the probability of getting a 6 times the probability that the other one ends up being a 6? And that ends up being also 1 out of 36, which is about 3% of the time. So if you play a lot of board games and you roll 2 dice, do you know that getting a 6 is not that likely? Isn't it only going to happen about 3% of the time then you do it? Which means it stands out a lot, doesn't it? Oh, I got a 6, right? Independent, multiply together. Dependent. You put an E in dependent. Yeah.
Can I ask a question?
Go for it.
What you just said at the bottom of your page there with the 6s, that's
Yeah.
still in independent?
Yeah, because you roll the first dice as in a 6, and then you're about to roll the second dice. Would you agree when you roll the second dice, it doesn't really matter what happened to the first dice? It could have been a 6 or not. It doesn't matter. Isn't the next row still going to be, an independent event? Right. Getting a 6 has no effect on the previous result. Right. That makes sense. I'm not sure I'm phrasing it clearly, but that's what I mean.
Because you have 2 dice.
Well, if you have 2 dice, that's even better. Would you agree if you threw both dice together, which is probably how you would do it physically, right? Won't the first dice roll randomly and turn over to what it is, and won't the second one roll totally independent? It's not like they're little magnets, and when one's a 6, it pulls the other one over to it. Right? That would be cheating, right? They are independent, right? Right, let's dependent, which is the same thing as saying not independent. Well, here is an example of that. I'm going to do a card game. And we're going to, I'll give you some details behind this. You've got a deck of cards, right? So here's my deck of cards. And I'm randomly giving them a good shuffle, and I'm going to bring a card out, and it's going to go here. And we talk about without replacement. Almost all these questions are without replacement. Do you know when you shuffle cards and you deal someone, you don't take the card back and then shuffle it and give them another one? That's not the typical way you play games, right? Don't you give them a card and then you give them a second card, right? So you give them a card and then you give them a second card. And we want to know what's the probability that you get dealt 2 aces. So that would be pretty good hand. You know, if you play cards, 2 aces is a pretty good hand to get, right? So you might want to know what the chances of that happening are. And that is much more difficult to do, because if the first card is an ace, isn't the second card got fewer opportunities to be an ace? Can you see that the first event does affect the second? So to be able to answer that question, we have to find a thing called conditional probabilities. So I'm going to come back to that question. But before that, let's look at what's called a conditional probability. So here's an example of one. What's the probability that you get a king given that it was a club? So you read that out, that funny symbol there is given that. So that's an example of a conditional probability. I'm saying to you, what's the chances I get a king given that it's a club? So can you imagine somebody cheated and they said, I can't quite see what it is, but I can definitely tell you it's a club. Do you notice that that changes the probability numbers? Now, since I know that it's a club, doesn't that mean there's only 13 cards here? Great. Of those 13 cards, right, the clubs, because I know that clubs have happened now, how many of those are kings? How many of the 13 clubs are kings?
Would be one.
They're only one. Now, in that particular case, did you notice that the probability of a normal probability, just getting a king, right, with no other information, isn't that 4 kings out of 52 cards, that is equal to 13 as well? Do you see that in both these cases, the chances that you get a king are identical? So do you know that person who cheated and had a quick look and said, oh, I saw it's a king? Do you know that doesn't actually help you get a king more or less, right? So technically speaking, getting a king and a club are considered independent events. Getting a king and knowing that it's a club, they have no effect on each other. One does not affect the other. It's a kind of interesting thought. So let's go back to this fella then. I am going to find the probability that the first card is an ace, just that. Now, on a normal deck of 52 cards, there are 4 aces. Would you agree that the probability that the first card is an ace is 4 out of 52? Now, what's the chances now that the second card is an ace? Now, we would write that down, it's a little bit messy, but what's the probability that the second card is an ace, given that you already know that the first card was an ace? Well, when you come to do the second card, right, you shuffled them, you're about to turn over the second card, isn't there only 51 cards now in the deck? And how many of those 51 cards are aces?
3.
3.
Do you see that these two are now no longer the same number? That is different from this. So when you want to get the probability of an ace and another ace, it's 4 out of 52 times 3 out of 51. Do you see that it's 2 probabilities, but one of them is conditional on the previous answer? And this ends up being some ridiculously big decimal. So I'm not even going to try and make it a fraction. I'm just going to go 4 divided by 52. That's the first guy. I'm then going to go times 3 divided by 51. That's the second guy. And the answer is about 0.005 if you round it off to 3 decimal places. Do you know how tiny that is? It's like a 201 chance. So if you got a game, you know, get a deck of cards and you gave them a quick shuffle and you turn over 2 cards, the chances that that is a double ace, right, 2 aces in a row, is only going to happen 1 out of 200 times. That's essentially what that decimal tells me. So can you imagine that you're playing poker and you're dealt 2 aces? Can you see why 2 aces is really good hand? Can you see why in that case the person would probably gamble a lot of money? Because the chances that the other guy has got the other 2 aces right, and is likely to beat you. Can you see in that case, it is very, very unlikely, right? And so you're really, if you gamble in the two obvious games that use probability a lot are professional gamblers who play poker and professional gamblers who play blackjack. Because you looking at your hand, and I don't know if you know blackjack, but suppose I get 15 and I'm looking at the opponent, right? I can see the dealer and I'm thinking, what's my chances of getting a card that's not going to bust me, right? What's my chances? Well, I already know 2 cards, right? I'm looking at them. Can you see the third card is going to be a little bit different? What's the probability? And then you do that quick calculation and you basically say to yourself, is it worth the gamble or should I stick? And good professional gamblers have got like an inbuilt calculator in their head. They play the game so much that they look at it and they know, stick, you know, give me a card, whatever. Of course, none of you who are under 21 should be applying any of these rules until you're allowed to. So don't zoom down to Vegas, lose all your money, and then come back and say, but you told me that this is what you could do, right? Okay, now, let's do another one of those conditional probabilities. Card games are good for conditional probability questions. What's the probability that I get 3 kings? So that's going to be the probability that the first guy is a king. Then it's the probability that the second guy is a king. And then you multiply the probability that the third guy is a king. Do you see that these are conditional probabilities? Because won't the first king get used up and then so on and so forth? There is a kind of cool pattern to this, so let's see how it works. The first card, 52 cards, 4 kings. That can happen 4 out of 52 times. Great. Now, second card. How many cards are in the deck now?
3.
51.
Yeah, I heard the 3 and the 51. You all agree?
Yeah.
Now, next card. Isn't there only 50? And there's only
2.
2. So, do you know if you were playing poker and someone dealt you 3 kings, you have to have a poker face? I don't have one. I'd be going, wow! Because I can tell you right now that that is going to be tiny. Would you agree? That is going to be one darn small number. And small means really unlikely, right? So when it does happen, it's a good event. So just for completeness sake, I'm going to do that 4 times 3 times 2. And then I'm going to divide it by the other guys. So 52 times, well, 51 times 50. And the number is so small that the calculator is saying that, which means 1, 2, 3, 4. That's how I do e to the negative 4. That basically is the calculator trying to tell you that, right? The scientific notation. So isn't that 4 zeros, 1 8?
Do you also have to look at conditions too? Like if the conditions, if somebody say isn't a good shuffler or things like that, does that have any?
Would have an effect, but I don't know how you could factor it in.
Yeah.
I mean, you can't factor in that the guy's cheating and got 2 aces under his sleeve, right? What's the probability of that happening, right? You can't really factor that in. So
Just look at them up and down and be like, yeah, you're that type.
yeah, well, I guess you could, right?
Yeah.
So are we comfortable with independent events? You can just multiply the probabilities and don't worry about what each one is because they're separate from each other. And then you've got this situation where one event has a direct effect on the other. I'm just going to do one more. Do you know in blackjack, getting an ace and a king is blackjack? There's other blackjacks, but that's one of them. It adds up to 21. You've won. It doesn't matter what the dealer gets, you win money, right? So That's the probability that the first card is an ace multiplied by the probability that the second card is a king. Now, we've done enough aces to know that's 4 out of 52. What about kings? Well, isn't the first card an ace? Right? That means there's only 51 cards in the deck. How many kings are there?
4.
4. Do you see in this case only the bottom number reduced? Just in case you get into the habit that the bottom's reduced by 1 each time and the top reduces by 1 each time, because it doesn't necessarily end up that way, right?
So is it still a dependent, right? Because
Oh yeah,
it
they're
is-
still dependent.
Okay.
The first card being an ace did affect the probability because it now means you've only 51 cards to pick from. So it did change it, right? It would have been 4 out of 52 and now it's going to have to be 4 out of 51. So it did alter it a little bit, but it did alter. And I said that was the last one, but I just decided one more. What's the chances you get 2 red cards? So it's a probability that the first one is red multiplied by the probability that the second one is red, right? Okay. There are 52 cards, as we know. How many are red in colour?
26.
I hear that. Well done. Now, that red card has happened. There's now only 51
25.
cards. And what goes on the top?
25.
I agreed. So those are not particularly horrible numbers. So I'm just going to turn that into a decimal to see how many times, or you know, what percentage, whatever you want to call it, what the probability, that's what I'm looking for. Do you know that that's going to happen 0.2? If you round it off to 2 decimal places, it's going to happen about a quarter of the time. Which seems reasonable, right? A quarter of the time you're going to get 2 red cards. Do you know a quarter of the time you're probably going to get 2 black cards? And about a half the time you're going to get 1 each. Or you know, a black and a red and a black. I'm grouping them together. So a quarter and then another quarter gets you a half. Now that is 2 events happening. The next fella we're going to do, I'm going to find a little guy I did earlier for another class. Oh, sugar and spice. Did you notice I didn't swear there? See how good I am? Okay, I can do it again. It's just going to be a bit of a pain if I don't find this in the next few seconds. Okay. There's a bunch of questions that they deal with which involves rolling 2 dice. So, because that happens a lot in games like like craps and Monopoly, right? You roll 2 dice, right? And so what we have to do here, and that's a table that I already had, and now I'm going to have to do it again. 1, 2, 3, 4, 5. Here we go. 6. And then 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, that'll work. And the first dice could be a 1, 2, 3, 4. 1, 2, 3, 4, 5. I was really close to losing it there, but I held on, right? And then the other dice could be a 1, 2, 3, 4, 5, 6. Each one of these boxes is one example of what can happen when you roll 2 dice. Just randomly. See if I pick this guy here, wouldn't that be the first one is a 4 and the second dice is a 3, right? Now, if I had time and then the other one I did, I color coded them. But for speed, I'm not going to do it this time, right? So this is going to be 1, 1, 1, 2, 1, 3, 1, 4, I'll be here all day. 1, 5, but I do need these guys, so there's no way of avoiding it. 1, 6, then 2, 1, and so on. As I go through this, do you know that there is going to be 36 different situations, different ways in which 2 dice can come up? As you go through these, hopefully I don't screw up anywhere. There is a distinct pattern, right? Do you notice that every row has a 4 in it, for instance? And every column, the second number is always going to be the same. You know, there's a lot of symmetry in this table, right? It's not just random digits all over the place. Almost done. Now you might want to make a copy of this guy, or if you don't want to write it like I have, maybe you could just go online and do a search like table of 2 dice throwing, and someone will have created a PDF and you could just print it, right? And that would be quite helpful, because we can use this table to do some more complicated probabilities. So here's a whole bunch of dice throws, right? And let's look at some interesting probabilities. What's the probability that you get a total of 3? Now, in many dice games, you might throw 2 dice, but don't you typically add them together and get a score? You know, like snakes and ladders or whatever you want to call it. Now, in this table here, how many choices were there? Well, there are 36 things that can happen. So that's guaranteed in this case to be my bottom number. But how many of those 36 give you a total of 3?
Two.
Yeah, that one and this one. Agreed? 2, 1 adds up to 3, and 1, 2. And you recognize that those count as different events. Can you imagine one of my dice was blue and the other was red, right? So a 1 and a 2 is not the same as getting a 2 in the first one and a 1 in the second, right? So we're doing this as a counting process, right? We're not doing right now any kind of conditional probabilities. We're just saying, like, this is 36 things. How many of them add up to 3? There's 2 of them. And as a decimal, let's see what that looks like. It's about 0.06 if you round it off. About 6% of the time, you're going to get a total of 3. Right, here's a question for you. What total has got the highest probability of happening? What total has got the highest probability of happening? So it's more likely to happen than any other total.
7.
I hear 7. Any other choice? If it wasn't 7, what do you think it might be? Because a lot of people pick this. Yeah. Now, the correct answer is 7. You were right. But a lot of people who don't understand probability or the fact that this table is helpful think that 6 should be the most common. And I think there's a lot of sense behind why they should think it's 6. You think of a dice, right? Isn't the first one 6 numbers? Half of that is like 3, right? Isn't the other guy got 6 numbers on it? Isn't half of 6 3? Can you imagine 3 from the first one, 3 from the second one adds up to 6? You know, that kind of argument. It's kind of pseudo-sensible, isn't it? But it's not actually the correct answer. So let's do this one first. How many ways can you get 6? If you do enough of these tables, do you notice that totals tend to be in the same diagonal? I'll show you what I mean. That one, that one, that one, that one, and that one. Do you see that diagonal? Right, so that adds up to 6. There's another one, there's a third one, there's a fourth one, there's a fifth one. You only get 5 out of 36. And 5 out of 36 is about 14% of the time. Getting a 7, which is this diagonal here, there's actually 6 ways that that can happen. And that's about 0.17. So if you roll 2 dice, do you know about 17% of the time you're going to get a total of 7, but only 14% of the time are you going to get a total of 6. What's the hardest thing to get? What's the hardest total to get when you roll 2 dice?
2 or 12?
Yeah. Do you know you can only get a 2 one way out of 36? And can't you only get a total of 12 one way out of 36? So both of those are very rare. They're roughly about 3% of the time each. Now, I know there's a game called Craps, and I do love casinos, but I do not play craps. I don't understand the game. And when I go to the casino, I like to go to the casino not to think. So I don't actually sit in machines and start working out probabilities and that, because then it would just become work. I like hitting, I call them puggies, you know, the machines with bright lights. If it's got bright lights and it plays music and makes funny noises, that's the ones I like, right? So I know that if I went and I spent time, I could figure out how to play craps. And I'm sure that within that, there is a lot of probability decisions that you would make about which way you should bet for or against the person who's about to throw the dice. Because I believe it, at least I know that part of the game is that only one person throws the dice, but lots of people bet on what's going to happen when he throws it, right? So for instance, if I throw he's going to get double 1, which is what, Snake Eyes? Snake Eyes? I got a name, Snake Eyes. And that's probably bad news for him. But if I bet that that's going to happen, wouldn't that be good news for me because I'm going to win some money? So if you know the probabilities of things happening, can't you judge how you're going to bet and what you're going to bet on?
I'm guessing that's where lucky number 7 came in, right?
Because 7 happens a lot. So people,
yeah.
There are probably a group of people, I'm making this up, but there's probably some truth in it, who play craps. And do you know the only bet they play is they put their money on 7. And they let everybody throw the dice and they can do what they like. But, you know, they're going to win 17% of the time, right? And you'll get more than your money back, right? I bet you if you did that, they might give you like 6 times your stake, right? And because in tables like that, the edge that the casino has is very small. When you play the machines I play, and I know this, that the payout rate is 80% roughly, which means that they are designed in such a way electronically that on the long term, you only get 80% of whatever you play. On something like craps in the casinos, the edge is very small. It's like 98% back. So you could play forever on a roulette table. And if you're sensible, you could probably play forever on a crap table and lose, but lose quite slowly. On the other hand, if you play the games I play, you lose quite quickly. But they're fun while it lasts. Any questions? So we are looking at probabilities of getting totals using the dice. Are you comfortable? I could ask you things like, what's the probability that the total was an even number? What's the probability that the total was 8? What's the probability that the total was a 3, 4, or a 5? Wouldn't it just be the bottom number's 36 and you just scan through all these ones and you count all the ones that work? So just out of randomness, this is me just picking a weird one. What's the probability that one of the dice is a 6? In fact, I'm going to phrase it a little bit better. Exactly one of the dice is a 6. So, bottom number is 36, because it always is in this version. In this table, how many of those combinations have exactly 1 6 in them? Well, that I said exactly so we'd kick out the double 6. Right, that's how I phrased it that way. because that doesn't have exactly 1 6, it has 2, right? So that's what my phrasing was meant to be. Can you see there's 5 here and 5 more here? You see your answer is going to be 10 out of 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you're done. And I could say, what's the chances that your total was, you know, bigger than a 5, or your total was 1, 2, or 3, or any of the others? And won't it just be a matter of scanning through these and counting out of 36? So that's done. Right, that kind of question is done. Now I'm going to keep the same table, but a much more complicated version of it. Let's do a conditional probability. What's the probability that you get a total of 7 given that one of the dice is a 4? Now, you're being told that one of your 2 dice is a 4. And now you're going to calculate the probability that the total is a 7. Right? So, since I know this event, this table doesn't turn into 36 choices now. Doesn't this table just turn into the choices that have a 4 in them? And it makes a kind of cross symbol. Do you see there's some guys down here that have a 4 in it, and the guys along here have a 4 in it? Now, don't do this. Oh, I got it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The bottom number is 12. I did something wrong there, didn't I? They're not 12 answers, 12 things. How many are there? Well, I'll do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I did something wrong there, didn't I? Didn't I count that guy twice? So be careful when you count this guy that you don't double dip, right? You don't count twice. Now, only out of those 11, I wish I could put circles around this, but if I did this, the picture would get really ugly quickly. So here's a pretend circle. Can you imagine a big circle here and a big circle going this way? How many of those things, how many of only those 11 add up to 7? Well, let's see what would happen. That one adds up to 7, agreed? Nothing else does. How about that one there? Doesn't that add up to 7 and nobody else does? Isn't the answer 2 out of 11? And I'll turn that into a decimal. And 2 divided by 11, it's going to happen about 18% of the time. What's the probability that you just get a normal total of 7? Oh, 17% of the time. Now, can you imagine that I'm an unscrupulous gambler and I get a special dice, and I get a dice that is designed in such a way that 4s happen a lot. You know, like normally you can get a dice, if you roll it, you always get 6s, or if you roll it, you always get 1s. But let's suppose I'm being really sneaky here, because the casinos are looking out for those kind of dice, right? Hey, that guy keeps on getting far too many 6s. Let's have a look at these dice, right? That kind of trick. So imagine I do it so it's a 4. Right, lots of 4s happening. Can you imagine that 4s are not going to get noticed the same way that lots of 1s happening and lots of 6s happening? But isn't that edge maybe enough that I will win more than I will lose? Because you don't just get your money back, you get like 7 times your money back. And if the casino is only working on a very small percentage, in the long term, that could certainly help me. Right. Just a thought. Don't do it, it's illegal. But you can imagine probabilities can work that way. Are we okay with my dice guy and totalsy things and using that, and then how you can use it for conditional probabilities? That's a little bit rarer, but I did want to show you one in case you came across it. Is there any questions before I start looking at the homework questions so we can see what kind of stuff they've got? Because they do have some things that we haven't covered.
I was wondering
Mhm.
why you multiply independent and dependent events instead of add them.
Oh, it's interesting. Well, can you think of probability as a fraction of time something happens? So if half the time the first thing happens and a third of that one half is the second one, can you see a half times a third would be how many together that would get you?
I think so.
Okay, let's do a different, let's show you a silly question to show you why adding wouldn't work, right? Suppose we looked at getting 2 heads, agreed? Would you agree throwing a head has no effect on what the next coin's going to be? So they're independent. So I'm saying you take the probability of a head and you multiply it by a probability of a head. And since they're an independent, I can just come up with the answer 1/4. Does it seem reasonable that if you threw 2 coins in the air, about 1/4 of the time you would get 2 heads? Right, so that seems reasonable. Now, suppose we did this question, but we thought that you should add them together. Do you see that what you're saying is that the probability of getting 2 heads is guaranteed? It's 1. And would you agree that that ain't true, right? So the logic of it tells you that multiplying works and adding doesn't, right? Just by the simple, thought experiment that I did here. Now that helped.
Yes, thank you.
So let's zoom in and see what we can do here. Have I told you a joke lately? Because I got a feeling I might not have. So do you want a joke? Do you know you're getting one even if you say no? But at least I'm giving you the opportunity to say no before we do it. I'm just getting set up here, so if you can hold off a few seconds, I'll find out if I've got any thumbs up. I have enough thumbs up, we're going for it. Jenny, did you do your thumbs up anyway?
I just nodded my head.
Nodding will do. Okay.
Did you say Jenny or Jennifer? Sorry.
I said Jenny.
Oh, I don't know if you call me Jenny or Jennifer.
Oh, you maybe go by Jennifer. I'm only going by the name that's on the screen here.
Oh, okay.
So Jenny is Jenny and you are Jennifer.
Oh, okay.
That probably will make life easy if I want to ask someone a question. I know there's 2 Rachels. Where's the other Rachel gone? Where are you, Rachel?
Right here.
I'm also right here.
Oh God, I can see it. Yeah. Do you know that celebrity squares?
Yeah.
You're like in the opposite corners of each other. It kind of looks like that sometimes when I do this. Okay, so want to tell you some Canadian jokes because I haven't picked on Canada yet, have I? Okay, you ready? I'm not sure I've actually edited out all my jokes, so you may end up getting to hear this again if you watch this video for revision purposes. So, what's the difference between a Canadian and a canoe? Canoes can tip. Oh, I have got some, I appreciate that humour. Do you get, I was told, this was a joke that was told to me. So they told me that evidently Canadians are not very good tippers. So if you work in the restaurant industry, evidently that's a truism. Is that a truism or is that just a nasty thing to say about Canadians?
It's just a nasty thing to say about Canadians.
Okay, is that because you're Canadian?
Yes.
Okay.
I think also it's because the Canadians, they include that when you buy stuff, it's included when you're purchasing or you're going to a restaurant, it's included with your bill. So they don't tip because it's included.
True story. The first time me and my wife went to Paris, it was nice. When you lived in Scotland, you could fly to Paris in about, what would that take? About 2 hours. So it wasn't a long journey. So we went to Paris for a week and can't remember if it was a weekend. But anyway, we went to Paris, and I didn't know that in the French restaurants, they add the service charge, which is basically the tip. And I was tipping them on top of the tip, and I didn't even realize that it was already extortionately expensive, right? You know, Paris is extortionately expensive. And I was tipping on top of the tip. I have learnt that mistake. So evidently, you can still tip someone, but you typically only do it with like the coins that are left over, seems to be the culture. You know, so if you get whatever it was, 82 euros left, and you leave that because nobody wants to have coins all over the place. So they do that. Believe, but don't quote me on this because I should have known and I've forgotten, but I believe in Italy they do the same thing. So it's probably quite a European thing to do. In Britain they don't. So if you do go to Britain, will you make sure that you do tip the person, because they don't get anything on their thing. And I know they don't do it in America, so I definitely do it for that reason. Now, back to jokes. Are you ready for this one, Zoe? Did you hear about the Canadian who get killed raking up the leaves? He fell out the tree. Okay. Last one, and then that's it. Canadian was walking down the street in his little town in Canada and had a big crate of beer on his shoulder, and he was dead happy, and he's walking down the street, big crate of beer. And across the road he sees his friend, and he waves at him, and his friend waves back. And then his friend says, "What's that you've got on your shoulder?" And he looks and he says, "It's a crate of beer for the wife." And his friend said, "That was a good swap." Okay, mixed reactions to that one. I think that's all my Canadian jokes over with, so you are surviving. We have some chat here. Oh, God. Yeah, someone says as a Canadian, I disapprove, but they were winking, so that's fine. I'm a great believer that jokes should not be unsuitable, and I don't think that's unsuitable. I think it's fair as long as I insult everybody. I have quite successfully insulted Scottish people, would you agree? Or at least Scottish husbands. I've definitely done that quite a bit. So I've added Polish. Have I done any Polish jokes yet? Okay, since I've said that, I've insulted the Canadians. I'll insult the Polish just once, just to show you that I'm an equal insulter, right? How do you stop a Polish tank? Don't know? Shoot the people pushing it. Zoe, you have got a very stoic face, or the screen has frozen, one or the other. You didn't like that joke? Don't tell me you've got Polish ancestry. I'm going to get sued if this keeps up. Okay, we are out of that. I'm not going to think any more jokes, so we'll never get this thing done. Okay, so we should be in here. Right. So hopefully you are all looking at homework 4.2. Okay, let's see what we have here. Question 1, if two events are independent and you know that one of them, P of A is 0.5, what is the probability of A given B? If two events are independent, knowing that B has happened should have no effect on A, agreed? So shouldn't the answer still be 0.5? So if two events are independent, the probability of A and B is the probability of A times the probability of B. That's one way of testing it. But the other one is the probability of A given B will be the same thing as just the probability of A, right? They have no effect on each other. Same answer. It's a bit like me saying, what's the probability that I get a head when I throw a coin, given that it's Tuesday? Right, would you agree the day of the week has no effect on the probability of a head happening? Would it still be the probability of getting a head? Still be a half. In question 2, these two events, A and B, are mutually exclusive. What's the probability of A or B? So what do you do to find the probability of A or B? And I'm writing this down as this is happening. How do you get A or B? Do you add or multiply the two things? That's your choices, really.
Add.
You add them. And if they are mutually exclusive, don't you just add probability of A to the probability of B? Agreed? And if you did that, wouldn't you simply just do 0.3 plus 0.5? And you'd get an answer that looks something like 0.8. Wouldn't that be the answer? The 0.8 would be the answer. Now, if I tell you that the probability of A and B is 0.1, aren't I also telling you then that they're not mutually exclusive anymore? If it was 0, they would be mutually exclusive, right? If A and B had a probability of 0. Now that means that we have to adapt the formula. So isn't it the probability of A plus the probability of B, and then don't you subtract the probability of both of them, right? A and B. So as a calculation, if you tell me that the AND probability is 0.1, I'll start off with the 0.3 add the 0.5, but then won't I subtract the 0.1? Subtract the AND part. So in this case, the answer will actually be a little bit smaller. Does that make sense? The difference between two events mutually exclusive and two events that have some kind of interaction. Right? Now, the next one looks similar, but it's not mutually exclusive. It's using independent. Okay, if two events are independent and you want to find A and B, do you add the two probabilities or do you multiply the two probabilities? Which is kind of bringing to Maria's, remember Maria's question 10 minutes ago or whatever. What do you do when it's A and B? Add or multiply the two together to find the probability.
Multiply.
You multiply. So you would go something like 0.2 times 0.6. So the answer in this case would be, what, 0.12? Agreed? Now, I'm going to have to come out of this to show you the last part of this question. P of A is 0.2. P of B is 0.6. P of A given B is 0.9. And we're being asked to find P of A and B. And I will leave and come back in, because this is a guy that I haven't shown you. We've done conditional probabilities and we've done ANDs. What we've not done is that there is a connection between an and a conditional probability. Now, we've done those questions, but without using the formula. So remember those questions where the first king card is a king and then the second one was a king and you adjusted your probabilities accordingly. Remember that kind of situation? Right. That's what this formula is basically saying. It's saying that the probability of A and B is the probability of A given B times the probability of B. Strangely enough, textbooks tend to write the formula that way around, but it has the same effect. I mean, just switch places, right? But that tends to be the way you'll see it in a textbook. So let's see what that means. Do I know A given B? Yes, it happens 0.9 of the time. Do I know B? Yes, it happens 0.6. So A and B is 0.54. So can you imagine that if I give you any two of these three, can't you find the other one? So if I told you this guy and this guy, couldn't you find him? If I told you this one and this one, you can definitely find him, right? Can you see in this way, you don't need to be told a story about cards. Can't you just be told numbers and plug them in and see where they go? So let me create a random question that might look like that. Suppose I tell you that the probability of A and B happening is 0.2, and that the probability of B happening, I'm trying to make this darn thing work and it's not easy to do, but I should be able to get it, is 0. B, what do I want you to be? 0.2 by 3 by 3 times something big, 0.3. And they asked us, pardon me, to find that guy. Now, you couldn't do that question in a normal sort of a way because they don't tell you it's kings and queens, so you can't theoretically figure out what the numbers are. Do you see? You can only use formulas. So the formula that we're going to use is the one I just wrote down here. The probability of A and B is the probability of A given B times the probability of B. There's something about that order that just is easier for my brain to remember, right? You could write it the way the textbook does it and it's fine, right? But let's see what we get. Oh, I know this guy here is 0.2. I don't know this guy, but I know that I'm going to multiply it by 0.3. Can you see that if you have a formula where you know 2 out of 3 things, can you always find the third thing? You just have to figure out what calculation is going to do it. And I have a rule that I use in algebra a lot, and my rule is called, as long as you do it to both sides, it's okay rule. Made that name up, but I like it. As long as you do it to both sides, it's okay rule. So what do you think I should do to both sides here to find out what this is equal to?
Divide by 0.3.
Great. And isn't that what calculators are for? And if you do that, can you trust me? You now have your answer. So some probability questions do not involve stories like dice being thrown and you're adding up the total, or kings and decks of cards, right? Or throwing coins in the air and getting all the various combinations, right? Not all of the questions end up being like that. Can you imagine there are going to just be some where they tell you information with no story background, but nonetheless you can still find things, can't you? Because there are some formulas that show you how these are all connected to each other. Are we cool with that, or do you want me to do another one of those made up ones? I'll make one up for the next one.
I have a question.
Yes.
Is the probability of A given B the same thing as the probability of B given A?
What a cool question. No is the answer. You would think it should be, but no, it's not. So let me think of an example to kind of make that happen, right? Oh, here's a very silly one, but it kind of proves my point. So the question is the probability of A given B the same as the probability of B given A? And I'm going to prove it by counterexample, which basically just means I'm going to show you an example where it doesn't work, right? Where it's not true. So let A be, you get a king. So you pick one card from a deck of cards and it's a king. And let's B be that you have a face card. Now, if you're not sure what a face card is, Jack, Queens, and Kings are face cards. Okay? So let's look at what the probability of A given B is. That is, what's the probability that you get a king given that it was a face card? Okay, since it's a face card, and face cards are Jack, Queen, and King, and there's 4 suits, would you agree there's 12 of them altogether? Right, there are 12 face cards in a deck. So in this conditional probability, whatever that is, that's the bottom number, right? That's how many times it can happen. How many of those 12 face cards are in fact kings?
4.
Right. Right, Jack, Queen cards, thingies, right? Which becomes eventually 33%, right? Let's switch the order. What's the probability that you get a face card, right, given that it was a king? How many kings are there in a deck? There are 4 of them, right? So there are 4 kings here. Of those 4 kings, how many of them are face cards? Right? Can you see one way around the information, the thing that you're looking for could happen 33% of the time. But if you switch the information, right, you switch what you're told and what you're trying to find the probability of, as we did here, do you see that the probability is now totally different? In fact, in this case, isn't it guaranteed that you're going to get a face card if you're told that the card is a king? Right. So you're about to deal the card, but the dealer has a look at it and says, oh, by the way, it's a face card, it's a king. Isn't your chance of getting a face card now guaranteed? Because kings have face cards, right? Now, if you switch the story around, he's got the card and he says, oh, it's a face card here. Isn't your chance of getting a king still only 33%, 4 out of 15? In one case, it's guaranteed, in the other, it's not. Do you see that they are switched round? Because this one here is basically B given A. And you see it's not A given B. Cool. It's a very good question. I wish I'd thought of that question. Right, so let's go back in now and see what else I've still to do. These are good questions. You might not like them, but I like them. And what you've got here are 2 events, and then you've got a probability. And your job is to turn this English sentence into one of these equivalent probabilities. Now, A is the driver is younger than 25, and B is they got a speeding ticket. So the first question was the probability that the driver has received a speeding ticket and is under 25. Now, in the English language, you wouldn't probably pay a lot of attention to that word and. But in probability, isn't the 2 words and the other one or very important? Because they are actually going to get used in the question, aren't they? The way you write it. So the minute they said and, do you see that that kind of makes this the only one that works? Now, if I had 2 ands, I would look at each one and I would figure out which and went with the information that was going here. Right, let's look at B. The probability a driver is under 25-year-old has received a speeding ticket. Now, aren't you told this piece of information? Right? So think of every word like a lawyer would read a contract. A driver who is under 25 years old has received a speeding ticket. You're telling me he's 25 years old. Aren't you giving me a piece of information? Right? And what information are you telling me? Well, you are telling me, A. So what do we have here? We have a given A. So it's that one. What's the probability of B receiving his speeding ticket given is under 21? Okay, third one. The probability a driver who has received a speeding ticket is 25 years or older. Now, when I look at the conditional probabilities, do you see that these have, oops, missed it, this guy here and this guy here. What piece of information do you know has happened? He has received a speeding ticket. Isn't that given B? You're told B has happened. And so if I look at the given one, do you know that's my only choice? Now they've got a little thing called A with a C above it. Do you know that's a notation this textbook means for the complement of C, or another way of saying that is not C? Well, isn't 25 years or older the opposite of less than 25? So that's where that's C. So although I could have got that answer because it's the only one that had given B, the AC did help. Now this one here, even although I haven't read the sentence yet, do you see it has the or in it? What's the probability that a driver is under 25 years old or has received a speeding ticket? Now, out of that list, which one do I go to? Because it's the only candidate. I don't need to worry about any other choices. Only one of them works, right? Which one of these? Oh, I take it back. I just saw a second one. It might be that one there, right? Or that one there, right? So I guess I do have choices. I didn't realize that one was there. Now, the driver is under 25 or has received a speeding ticket. Isn't under 25 A and isn't the speeding ticket guy B? So it's this one. Suppose they had said, let's see what that one would be. That one would be, has not received a speeding ticket or is under 25. That's how I would read that one. Okay, last one. I'll let you think about it as I read it out. The probability that a driver has not received a speeding ticket or is under 25. Now the word or means it's this one or this one. Which one do you choose, the second or the fourth?
The fourth? Or, I'm sorry, the second.
Right, you changed it just in time. Why are you changing it to the right answer? What was, apart from that it's the right answer, what was your change?
Because the driver did not receive a speeding
Right,
ticket.
and not is a compliment. So do you know if you see the word not, be on the lookout for A, C, or BC, depending on which one is not. Right? And if they just say it the way it was written, it'll be an A or a B. Right? So you know I could go through combinations like, what's the probability that they're over 25, which is another way of saying not 25 or under, right? So I'll phrase it that way. What's the probability that they're not under 25 and they did not get a ticket? Wouldn't that be an AC or BC, right? I've tried to do the notes in both cases, right? If you've had practice at doing this one, then question 6 is the same storyline. Now, this one is empirical probabilities. They've done it by collecting data and putting it into a table. And oops, I got 7 minutes by my watch and less by my computer. Do you see the or, isn't or and? And let's say it again, isn't or add, and isn't and multiply, right? So whenever you see an or, you're going to add some things together. Whenever you see an and, you're going to think of multiplying. In this case here, would you agree that these are all mutually exclusive? Green M&Ms are not yellow M&Ms, right? They're separate. So if you wanted to get any particular probability like green candy or blue, wouldn't you just add the green and the blue together and get 13%? Are they mutually exclusive? Sure. If you did an or, wouldn't you just add them together again? So, oh, that's a good one. Not purple. I like that question. If they said purple, wouldn't the answer be 20%? What's not purple?
80%.
Yeah, that's all. If purple is 80% of them, isn't not purple everybody else 80%? Good question. Made me think for a minute. Here's another story. The difference here is, do you notice that they haven't given you the percentages, which was really nice of them here. So when you come to do these questions, aren't you going to have to take this 111 and divide it by the total number, which I hope they've got in the question, otherwise I'm going to have to add it. Do they say anywhere in that sentence what the total number here is? Okay, I'm going to pretend it's 200 just for ease. If you want to know what's the probability that you just randomly pick one and it's between 3 and 9 feet, won't the answer be 111 divided by 200? Rounded to 2 decimal places. And in fact, won't all of these simply just be the relative frequencies of these guys? Because relative frequencies are equivalent to probabilities in these questions. Okay, question 9. You roll 2 dice, one's green and one red. Are they independent? Are 2 dice independent? Yes, nodding will do. I'll take nods. If 5 on the green and 3 on the red, couldn't you just multiply them together and get the answer? If you had your table in front of you, wouldn't there only be one situation where that was true out of 36 possibilities and you could get the answer that way? And that basically is just another version of the dice one up there. Question 11, do you know those questions we did sums? You know, what's the probability of the total? They're calling it a sum, but the sum is 10, right? The total is 10. Don't you just add them up in your little thing? So that's what question 11 is going to be. That's what question 12 is going to be. Right, question 13 is to do with cards, and we've done a lot of cards. So just as an example, an ace on the first card and a 10 on the second. Right, haven't we done things like that? And there's a little bit more worded, which is kind of nice. Wouldn't you go, probability ace first is 4 out of 52 times, what's the 10 on the second going to look like? Well, won't there only be 51 cards and 4 10s? So it would be 4 over 52 for the first one, times 4 over 51 for the second. And if you look back at our earlier video, didn't we do almost identical kinds of questions like that? So that's what's going on here. 14 is just some more practice at the same. 15 are just special versions of that. You just need to read it. It's going to be something out of 42 times something out of 41, but they're making the second card a little bit vaguer, right? So be a little bit aware of that. 16 is a nice table, so we're back to reading of answers and putting them in there. And they do give you the numbers, so I'm sure you can read that. We do have, I know I'm pushing the time a little bit, but this is kind of important, so I want to do an example of this, especially a lot of you are in the medical field are thinking about it. This table gives you a really good example of how probabilities can be used to analyze a test for something. So I'm going to go out and not use up their questions because I want you to get plenty of practice at it. So I'm just going to create my own pretend test. So let's suppose way back in the beginning, they were looking for an HIV test. And you have people who test positive, and you have people who test negative. And then you have people who have HIV, and people who don't have HIV, right? And let's suppose that you did a practice run, because if you're going to do a test, shouldn't you go out there and see how good a test it is, right? So you did a practice test, and this guy here was 500, and in this group here there was 100, in this group here there was 50, and this one here there's 150, there's 350, right? I'm trying to make the numbers easy to calculate. So this total here is 600, this total here is 400, this total here is 550, and this total here is 450, and everything matches up to a nice even 1,000 people. So you did a trial on the efficacy of this HIV test. Now, there are two very important probabilities that you typically want to know. You want to know the probability of a false positive, and you want to know the probability of a false negative. Don't know what they used in there. Negative. And those in the medical have probably heard those terms, and even if you have not, you may well have heard of it. So let me tell you what they are. A false positive is you go into the doctor, he takes your takes your blood, and 2 days later he gives you the phone call, and he says you've tested positive for HIV. It's called a false positive because you don't actually have it. The test just said you've got it, right? Tests are not perfect. You might think they should be, and probably you should be, but you know in real life they're not. Don't you get false positives? People who test for a disease and don't actually have it, right? Can happen. A false negative, well, that would be you're worried about, you've got HIV, you go into the doctor, he does a blood test, and 2 days later he gives you a quick phone call and he says, nothing to worry about, you tested negative for HIV. Now, the reason it's a false negative is that the test said negative, but you really did have HIV. Now, can you see that in each of these cases, there are consequences, right? They are errors. This one here, I would put much more priority on. Would you agree that for something like HIV, a false negative could be really dangerous? First, you don't think you have a problem. I'm healthy. Because the doctor told you, right? Negative. And you may not be careful about your activities, right? And cause danger to other people unknowingly, but still it's out there, right? It's a bit like saying you tested negative for COVID-19, right? Then you go and visit your auntie and your uncle in the old age folks home because, hey, I'm cool, I got tested just to be sure. But you weren't, you actually had it and you could give it to them. Do you see how that's a bad thing to happen all the way around? Now, what about the false positive? Well, it's bad for your psychology, but it probably won't kill you because you don't have the disease. The test just said you had it, right? You're actually healthy. So what you're going to do, you're going to probably come in because the doctor will get you in, right? And he'll do other banks of tests and he'll say, okay, that happens, false positive, sorry about that, no biggie, right? So can you see why I want this to be as small as possible? And that might be a bit big. Now you might think, well, can't we just arrange it so that's tiny and that's tiny at the same time? the rules are not very nice. Typically, if you make this really small, you will make this bigger. There's no way to avoid it. Show you what could happen. Suppose there's a scale of 0 to 50. So they take your blood and they measure something, and the measurements are 0 to 50, right? And they have to make a decision based on this number. And let's say they make the decision that 40 is a cutoff. Up here, you've got HIV, and here we'll say you've got no HIV, right? If you move this lever that way, you will definitely catch some of the people who've just got the start of HIV, right? They've only just had it for a short time. But can you imagine you're also going to have a lot more people who don't have it, who will also have that number? Because the populations basically look like this. Healthy people have that kind of number, and HIV people have that kind of number. Do you see, it's still spread from 0 up to 50. But if you do a cutoff point here, do you see you'll still lose a couple of HIVs? Do you see this side gets bigger? If you move it over here, don't you virtually catch everybody? But can you see almost 90% of the population now gets tested positive? So I could make an HIV test perfect as far as false negatives go. Every single person who gets a blood test, I tell them they've got HIV. Won't I be 100% correct for the people who had HIV? Isn't that a totally practical test? All you're doing is spending money and doctors' time and clinics and everything, right? No point. So can you see that in real life, you do have a problem? There isn't a perfect test out there. Some people, unfortunately, get false negatives. You want it to be as small as possible. So to finish this question, let's find the probability of a false positive. And now I'm going to also find the probability of a false negative. So what would that look like? It's a conditional probability. What's the probability that you test positive, right, given that you didn't have HIV? Okay, let's see how that would calculate. If you don't have HIV, aren't you one of these 450 people? You agree? You do not have HIV, you're one of these 450 people. So the bottom number is 450. Of those 450, how many of them tested positive? 100 of them did. And so this particular test, the false positives are 22%. So if you're totally healthy and you take that HIV test, 22% of the time the doctor's going to give you that horrible phone call and says you've got it. Or at least he's going to say you've tested positive, right, if they're being really particular. Now, what about a false negative? Now, doesn't that mean you tested as negative given that you actually did have HIV, right? You got it wrong. Now, if you did have HIV, aren't you one of these 550 people? So your bottom number is 550. How many of these 550 tested positive? Well, in this particular test, it's 500. So 500 divided by 550, and the answer you get is about 91%. So, did I count that right? My apologies. Yeah, given you and you tested, I chose the wrong number. My apologies. I'm getting old. It's 50, right? 50 tested negative, right? Tested negative. So 50 divided by 550. And what do we get here? That's 9%. That's much better. Well, relatively. What does that mean? It means 9% of people who have HIV are going to actually have it, but they think the test says you're okay. On this side, isn't 22% of the people who are totally healthy going to be told that they may have HIV? If I reduce this number, trust me, that's going to get bigger. As tests go, I'm not really happy with this test because I think that's far too big. And I actually think that's far too big. Now you might think, well, what's the problem with that? We have a finite medical infrastructure. Doctors only have so much time, and labs only have so much people working for them. Isn't there going to be a lot of time and doctors' effort involved in those 22%? Right, if you tested everybody in America, 22% of you are going to have HIV according to this test. Can you imagine how that would overwhelm the medical system? All those people would have to get checked, right, to make sure that they didn't have it. On the other hand, isn't that too big? I don't think 9% of people testing negative. So I would be very unhappy with this test. But you know, sometimes it's the only game in town. That's the only test that's out there right now. Now, I know that, take, for example, do you know the COVID test right now? Do you know there's not one COVID test, there's quite a few? See, for each one of those tests, these numbers exist. If you have a really bad test, don't you test thousands upon thousands of people and you say you've tested positive for COVID when they weren't even unhealthy? Can you see how that could scupper up all sorts of things? Like, how do we know someone's got COVID? Well, we know the ones who got to hospital who were ill with it. Would you agree they've definitely got it? And we know the ones who died from it because they died from it. But isn't there a whole bunch of people who tested? It was a false positive. And it was a false positive because they didn't have the disease. And because they didn't have the disease, they never got sick. But just to be really awkward, aren't there a whole load of people who catch COVID and don't get sick?
The asymptomatic, right?
The asymptomatic crowd. Do you see how difficult it is to get good data then? And how many people actually had or have COVID? Are they false positive or are they asymptomatic? Are you really willing as a country to spend a huge amount of money testing 360 million Americans when you might have a 22% false positive rate? Well, for just things, wouldn't every lab in America probably be working overtime for the next 6 months just to do that? And shouldn't they be doing other things like testing people's livers and kidneys and blood pressure and heart, but they can't because they're too busy testing for COVID? Aren't there a lot of doctors out there who are going to be spending so much of their time going through every single patient and giving them the test, checking the test, giving them, you know how disastrous? I mean, it's just the impracticalities of it. And I know people say that you should be tested, and certainly I have nothing against testing, but isn't the reality of it much more complicated than that? Because for starters, some people are going to test negative and have got it, and they're going to go out in the community and share it unwittingly. And aren't there going to be a fair chunk of people who don't have anything wrong with them and are going to quarantine for 24 days, or whatever it is, 14 days, and they shouldn't have bothered because there was nothing wrong with them in the first place. And sharing, because